Welcome to week 5 of developing my own UAV drone swarm without any experience. This week I'm going to continue looking in the requirements, some of the electronics, like the motors and the battery, and we will be looking at the payload size and some ingenious or stupid, maybe, ways of figuring out how big the boxes have to be. I'm focusing on what the drone has to be right now before I start building the drone, as I have been recommended by a lot of you. So, enjoy the intro. We are trying to develop an affordable UAV drone swarm capable of lifting 5 kilos per drone to deliver packages in dangerous areas like Ukraine's frontline or delivering food in the Gaza area. I am only 19, but I am documenting how I am achieving my dreams and how you can too. This is Navius. So the guy that did a bit of research for me last time, we actually continued and talked about motors. It was too much to fit in the video, but last week we figured out that EDFs are just way too power hungry. We would need a huge battery. Half of the battery was already more than the drone weight that we had as a target. It's not even possible. EDFs are apparently mostly useful for faster speeds, or at least not the stuff we're trying to do. So we're going with regular props. Now, the bigger the prop, the better, the more efficient, usually. I asked Cluster to do some research on the eCalc website. There you can do some simulations and find the best motor and propeller configuration for it to be the most efficient. Now, this guy is very smart. His dad did help him out. So they made an Excel sheet and somehow managed to figure how to test 4,000 configurations at once. Now, first of all, shout out to eCalc, amazing website. Second of all, shout out to Cluster, because I would have never been able to do this. It's amazing, okay? Look, so this is what we finally came up with. So this is the entire list he made with a little graph, and I'm still a little bit confused about this graph, but it has to do with efficiency. Now, he told me the top few are the most efficient. For example, this motor configuration generates 7,000 grams of thrust per motor, and it takes 96 amps for all 4 of them. So in total, that's 28 kilograms of thrust, which is more than what we need. So we do have to search for the efficiency curve because the efficiency is not linear. So this is our imaginary graph, okay? Okay, so this is no thrust, here's 50%, here's 100%. So it basically goes from no efficiency to way more efficient, and then it kind of plateaus and doesn't change much in efficiency. So currently we are looking at the max thrust, which is right here, which is 7 kilograms. Now, we don't need that much. If we are aiming for a 1.2 thrust to weight ratio, then we need a total thrust of 24 kilos, aka 6 kilograms of thrust per motor. So we need a whole kilogram less. So currently it's a bit hard to figure out where exactly on this curve we get 6 kilograms of thrust. So it's hard to determine how much energy that takes and if it'll be much more efficient. So let's go ahead and start with that. I'm gonna take you guys along. So first things first, we're going to determine the prices of these motors so we can rule out some of the motors that are just going to be too expensive. After that, we can look up the exact motors and we can figure out the efficiency curve and we can test it out in eCalc. So first off, we have this Scorpion motor. After a quick Google search, you can already see 305 USD, but if you click on it, there's a discount, which is a pretty nice discount. So I'm just going to do that with every single motor real quick. As you can see, the prices that I found go all directions. This one's pretty okay, pretty affordable. It's going to be expensive anyways, but yeah. This one's really cheap. I like this one a lot. So that's what confuses me. It goes from 750 to 120 for effectively the same thing. This could give us like a 1 to 1.4 thrust to weight ratio, I believe. Yeah, sounds good. So for the battery, I want to have enough for 2 hours of horizontal flight at roughly 20% thrust. And I want a vertical flight time of 10 minutes so you can land and take off. Now, you probably only need 5 minutes Because imagine how long 5 minutes is. I mean, in that time, you should be able to take off and land. Now, so basically, okay, I'm not going to show you all this because it's too much for in this video. But basically, I used ChatGPT to estimate some calculations about EDFs. And I figured out that 10 minutes of vertical flight with EDFs would take the equivalent power of 1 hour of horizontal flight, which is crazy, dude. So the current is not linear, so we're just gonna act like it's a linear to make an estimation, okay? So how do we work this out? So currently the motor is screaming like, give me 95 amps. And in return for the juicy energy it wants, it'll give us, how much? Roughly 7 kilograms of thrust, okay? But we don't even need 7, okay? Okay, so if we want 5 minutes of VTOL and the drone weighs 20 kilograms, then we at least need 6 kilograms of thrust, which is enough for a 1 to 1.2 thrust weight ratio. Now, that is not going to take 95 amps. So to figure out how many amps, let's figure out how much throttle we need. So 7 kilograms of thrust is basically the full 100%. So let's divide that by 100. And then we can just take 6 kilograms and divide it by 0.07. We need 85%. So we only need this part. So now let's go ahead and calculate that. So 95 amps times 0.85 is 80.75 amps of thrust. We only want this for 10 minutes. Well, actually, we only need 5 minutes. So basically, it's this number divided by 12 because 5 fits 12 times in an hour. So that brings me to only 6.7 amp hours, which is super nice compared to the other stuff we found earlier. So let's go ahead and calculate the horizontal flight. I think 4 kilograms of thrust should be sufficient to fly horizontally. I don't know how fast it'll be, but probably quite fast actually. So then we need to replace these 6, not by 4 because we have 4 motors. So we only need 1 kilogram of thrust. So let's just go ahead and repeat what we just did. So that's literally only 14.2% throttle. That's pretty crazy. Is only 13 amps. Okay, that's a huge improvement from what we just had. If this is true, then okay. So then for the 2 hours of horizontal, you just take this times 2 is 27 amp hours, making a total of 33.5 amp hours. Okay, that's crazy. Here you can get a 30,000 milliamp hour battery, which basically is all the requirements, right? Oh, it's only 1C to 5C? Holy. Then later I turned on my brain cells and figured out that 5C might actually be more than enough capacity, which could allow us to save so much money in space. But before I show you the calculation I made and why I think that, let's go ahead and talk about the payloads. So for this week, I thought it was pretty important to understand more about the minimum fuselage size so that it can still fit cheap batteries and other electronics. If we forget to consider this, then we might end up with a few size limitation when it comes to finding the right electronics. If we have a very unusual size request, that can make the electronics more expensive because it's going to be hard to find. So I asked Cluster to look into this and he's working on finding that out as we speak. He's just looking at a lot of different batteries and well-known products and finding out which dimensions it has. But I thought of another problem that we might encounter. Payload size. 1 kilograms of gold is tiny, 1 kilograms of feathers is huge. How do we know how big our payload is going to be, so we don't waste the 5 kilogram payload potential by just not having enough space for it? I've asked Aryan to help me figure out this stuff, and he made a quick list of things that seem important to fit inside of the drone. Then he figured out the exact dimensions and weight of those items, and I went into Blender to test it all out. So I made recordings for basically everything, but to be honest, I think it's way more fun to just show you what the results are. The first thing I wanted to test out is military food pouches, MREs, which is that food where you just put like water in, or you just heat it up. So it's pretty lightweight food and it's pretty big as well. This is 22 of them inside of the drone measurements. So this is the maximum wingspan and this is the maximum fuselage length. So it's quite big. It wasn't amazing. So this is taking up 150 liters of space. The bottom part is sticking out because the height is also put in here, the 20 centimeter limit, and that is 0.15 cubic meters. So then I thought maybe it's better to do it like this, and I do think it's better to do like that because then you have less wide fuselage stuff, but you also have more drag here, so I don't know for sure just yet. So then I tried one more thing where you just put some of that payload inside of the wings. I don't think that's a good idea. It'll just create drag and stop the lift from being there. And in comparison on how big this stuff really is, this is water bottles. So these are 10 half-a-liter water bottles. So in total, that's 5 liters of water. I don't know how many ounces that is, but each bottle is 16.9 ounces. And that is super duper small, as you can see. If we only have to transport water, that's way easier. And I mean, water is pretty important. That's why I kind of want to make multiple different sizes of boxes, or like payload boxes that people can put in the drone. Basically to make sure that if you want to transport water, you can just do it inside of the fuselage completely and reduce all of the drag. And for example, you will have these bomb bay doors that you can open up and then drop the package. But you can also slide in another payload box, a bigger one that's external, and we can try and do anything to make it more aerodynamic. I was thinking about these two things. Don't take it too serious, please. I just thought of this randomly. So I kind of want to make multiple sizes of boxes as well. So it's pretty good that I'm testing out the sizes of this. Then I thought of this. This is also 5 kilograms worth. It's 4 MREs and 8 water bottles. So in total, you will have 4 liters of water and basically 2 days worth of food. So the water is really the only limit here. I looked up how much soldiers drink, and that is between 3 to 4 liters per day. So this is enough for one soldier for one day. But I mean, maybe if they're a bit more cautious, they should probably be able to survive for 2 days on this stash right here. I'm not entirely sure though. I guess soldiers move a lot as well. But technically this should be able to feed and hydrate 1 to 2 soldiers, which is really good for one drone. I'm really happy with that. And of course, if this can feed soldiers, then it's also enough for people in the Gaza Strip. Water is just really making it heavy. And then this entire setup will be able to fit inside of the fuselage entirely, besides the water here. But it should be possible to put it in the fuselage. So that's basically everything I tested up to now until I turned on my brain yesterday night and I got a way better solution where I don't have to test all of these things out. I'll tell you about that now. I first want to establish exactly what problem we are even trying to solve. Okay, so this is a plane, all right? I drew this. So like I said, if you only want to transport bottles of water, it's probably only this big for 5 kilograms worth, so you can just fit it in the fuselage. Some items are way bigger though. So I'm not going to just make one huge box to make sure everything is able to fit in there. That's a stupid idea. I want to make roughly 10 different designs for different boxes that you can all buy on the website. But you need to determine which box is best for you. So what I imagine is like a calculator on the website. For example, if you want to transport MREs, you just give the size and the weight as well. Then based on that, the computer can calculate the density by just taking the X times Y times Z. So then you just take the weight of the package divided by the volume you just calculated. Then you get a 0.023 grams per squared meters density. So based on that, the computer can give you a density rating between 1 and 10. So for example, if the density rating box 1 is for 0.3 grams per squared meters, that matches up, right? So as long as it's not over that, it should probably fit in there. And then the computer will also check if any of these values exceed the values of this box's dimensions. If this box is 10 centimeters by 10 centimeters, then this is not going to fit. So we need to determine which boxes do we want to make. Warning, in the following content, I am making mistakes at almost every number I am saying, but it still explains the point I'm trying to make. Please don't look at the numbers, okay? So I think the best approach for this is using the data that we found on all of those items with specific dimensions and weights and stuff like that. Then we can determine the density rating for each one of them. And then we just take as many of these similar density rated items. So we have to determine which densities would fit in which density rating, basically. And then we basically have to make a box that fit as many of those kinds of items as possible. So I'm thinking about 90% because there's always going to be items that are just annoyingly shaped. Even things like mortars, you know, they're huge. They're very long, even though they might not be very dense. Like this will be way longer than this box will probably be, even though this could be in the one of 3 density rating. So the issue is the dimensions of everything is different. Let's say this is 30 centimeters. If we would make the box to only be like 50 centimeters, then this box would only fit inside of this box, in that axis at least, once, because there's just not enough space for a second box to fit next to it, because in this case you would only have 20 centimeters left. To counter this, we will probably have to make boxes slightly bigger than needed for a lot of cases. And that is why I want to divide the boxes into multiple density levels, because it gives a pretty good idea, I think, of how big the box should be. Because let me tell you real quick why I'm even calculating the density, because I think it's a little bit unclear. Obviously, our limit is 500 kilograms. If you know how many grams per square centimeters, you can just do 5,000 grams divided by, oh my god, I just put 5,000 kilograms, I'm sorry. So 5,000 grams divided by 2 grams, and then you have 2,500. So you need 2,500 squared centimeters to fit the maximum capacity inside of a payload. So let's go ahead and test out this theory. Because I'm pretty bad at math, I first of all had to ask Arjen. He made a spreadsheet with that formula in there automatically. So you just add your length, width, and height in there, and then you get the volume and the density. Also, you have to add the weight. Now, this is going to be very useful because we can just add a whole lot of items like we did here. Now, to be honest, these are a bunch of ChatGPT things. It just guessed what the size would be and the weight. We do have to check and see if ChatGPT is very accurate on that. I doubt it, so we're probably going back to manually checking. But based on this, we can really tell what the density ratings are like, and we can compare multiple ones together. To give you a better example, I see a few items here that are pretty close together, like this and this. So this is baby formula and this is bread, and the sizes actually are quite similar. As you can see with both items, there is one axis with 20 centimeters and the other ones are smaller. The same goes with this one below it, it's quite similar as well. So you could say if bread fits in this box, then diapers and baby formula will also fit in that box. So I think we should go ahead and try this out. So the first thing I did is take a few items that have a similar density. I was going to take bread as the main item and find items around that are quite similar. I wanted to select a range of items that are within the 0.1 difference in density. So for example, this item, bag of seeds, if I pick this, then the absolute largest item, or like the most dense item, could be this one. So these two items actually differ exactly 0.1. So anything in between this, I'm going to pick and try. So these are all of the items. So usually when you're designing a box, you would probably make sure to make the biggest item fit. Now in this case, I just wanted to see how accurate it would be if I just take the middle, like the first item. So I'm just going to take the dimensions of the bread in Blender, and then I'm going to make a box around the bread. Then I will take all of the other dimensions and find out if they can fit inside of the box whilst using all of the 5 kilogram potential. So first I got these 5 kilograms worth of boxes, which is meant to represent bread. And there are 10 pieces in total. I made the box around it slightly too big to just account for a little bit of wiggle room, but it's still not massively too big. So this is what it looks like. Now let's go ahead and test out the first item. So these were actually the seeds, so they weigh a lot more, and I only had to fit 4 of them. Now sadly, it did stick out of the box. That was pretty upsetting. So then I figured out that the other items I just tested weren't seats, but portable stoves. Yeah, it's pretty big. But the things I'm testing now are actually seats and they fit in there perfectly. So I have all of the results right now in front of me, but I think first we should talk about the battery capacity thing that I was talking about, because some people wanted to see that and are still waiting for it. If you happened to forget already, we were looking at a 33 amp hours battery with only 1 to 5 C. Now, all 4 motors need 95 amps in total, by the way, for all 4. And I was like, that's not a very good number. I thought it's like always very high. But last video, I learned the actual equation to calculate how much you need. Shout out to the person that told me that. Because of course, the C number is relative to the amount of amp hours you have. So in my case, 33 at 1C means 33 amps. So if the battery has a max of 5C, that means it has the capability of providing 165 amps, which is more than enough for the motor and a bit of like excess, I think. I'm not sure at what point the motor peaks. Let me check that out. Well. We might have an issue. I looked up the motors real quick and it says 115 amps max continuous current. So it doesn't make sense that 4 motors would use 95 amps. I think we did something wrong in the calculations. That's depressing. Now the C rating doesn't even matter. Let's just continue with the payload size. I'll just think about this next week. Well, that was actually pretty depressing. I hope you enjoyed that section of the video. Now let's go ahead and look at the results. So out of all things I tested, everything fit besides goddamn prosthetics and a portable stove. I guess it makes sense. But diapers, cooking utensils, baby formula, and bag of seeds is all able to fit in the same box as bread, which is nice. This is what I mean though. 90% of items you will want to transport at this density are roughly this size. You're not very likely to want to transport prosthetics or portable stoves anyways, but if you do want that, then you should probably just go for a higher density rating. We do have to make all of these calculations within the website though, so we should not forget that. Now, of course, let's take it with a grain of salt because these are sizes and weights estimated by ChatGPT. But it is pretty interesting and I do feel like my formula will be useful and I did not waste my time on that like I did with the motors. So I will continue working on this next week and testing out proper things with proper measurements because currently Arjen is working on getting more data so we can actually start testing stuff. Now, before we end off this video, Cluster did some very extensive research for me. So what I asked him to do was how big are the internal components that we need at least? And what weight is it roughly, and getting a rough price indication. So with the old setup, we only needed 1.5 liters of volume for the battery. That's probably not going to work. And the cost for all of the battery and the motors and everything would be 800 to 900 with the wiring included. But that is sadly probably not going to be possible. So for the control system, we need a flight control system, a global navigation satellite system, aka GNSS, an inertial measurement unit, IMU, a barometric altimeter, a terrain awareness and warning system, which provides real-time awareness of terrain and obstacle to prevent collisions or accidents. I think that's useful, but I'm not sure if we're gonna need LiDAR for that, but we'll look at that later. A radio control system as well, an onboard computing platform for processing sensor data, executing navigation algorithms, and making autonomous decisions. A telemetry system, or a telemetry system, maybe that's how you say it, which is like for transmitting data and stuff. A power management system, and maybe an emergency recovery system. Some UAVs have that, like a parachute or something like that. Of course, we need the automatic return to home features, so yeah, we'll look at that later. So here are the recommendations of solutions for all of these things. So I think in the future, if it's not too complex, we might want to make a custom board where you just have a lot of these items combined into one board instead. So I think with all of these separate systems, it should be a good indication of how much room there should be in the fuselage. If it ends up being smaller and lighter, that's only good. So here are the ChatGPT estimated like sizes and prices and all of that to quickly test out how accurate the predictions are. Here is one of the items. I looked it up real quick, and the size is 19 by 14 by 3 millimeters, and here it's 10 by 10 by 3. Close enough, okay? So based on all of that, even a parachute system, the total price range is approximately between 350 and 615 USD. He did go ahead and check out every single item individually, and he ended up with like 550 euros, which is 575 USD, I don't know, something like that. And the total weight is in between 120 and 105 grams, excluding any wiring or additional mounting hardware. So I think that gives you a pretty good idea. So based on that data, one axis should be at least 65 millimeters. The other axis should be at least 45 millimeters. And the height axis needs to be at least 20 millimeters. Oops. So that's actually really small. So if we would have a 3-meter wingspan and a 1.5 meter fuselage, plus 20 centimeters because of the wing, so 1.70 meters fuselage. In comparison, this is all to scale. This is what the electronics would take up in weight. So that's it for this video. Next video, I'm going to look further into the batteries. I want to consider a hybrid between LiPo and lithium-ion. And next video, I will be sure to use cubic centimeters instead of squared. I will also continue testing out more results. So see you next week. Oh, and by the way, I am making a Patreon. Please check the description to see if I already have one. I'm 20% of the way to make money with YouTube, but currently I can't. And soon I want to start actually testing out stuff in real life, and it's going to need some funding, sadly. There's a lot of stuff going on in the background that I'm not showing yet because it's not done yet. But when it's done, I'll show you the process and how we got there, so it's a bit more interesting to watch. So see you next week.